All right, I think we should get started. I know some of the people are still coming in because of we advertised the wrong room. So it is my distinct pleasure to introduce Professor Stephen Chou. He's going to come speak to us today. Professor Chou is the Joseph C. Elgin Professor, Department of Electrical Engineering at Princeton University. He got his Ph.D. in Physics and Electrical Engineering from MIT, a Master's in Physics from State University at Stony Brook, and his B.S. at the University of Science and Technology in China. Professor Chou's CV goes on for 59 pages, so I will just only hit the highest of highlights. He has an incredible number of awards and things. He's an entrepreneur in his spare time. He's founded or co-founded 3 companies, Nanonex, NanoOpto, and BioNanoMatrix. He's a member of the National Academy of Engineering. He has won the IEEE Brunetti Award. He's an inductee in the New Jersey High-Tech Hall of Fame. He won the Outstanding Research Award from the Penn Yan UN Foundation. He's an IEEE Fellow. He's a Packard Fellow. In MIT Technology Review 2003, he was featured in the 10 emerging technologies that would change the world. He won the Distinguished Achievement Award from the Chinese Institute of Engineers, USA. He has 24 patents, more than 40 pending patents. He has over 200 journal papers, over 220 conference papers, 160 plenary and invited talks, and 3 book chapters. Trust me, I'm only hitting the highlights. Just to describe his research a bit, for more than 28 years, he has carried out pioneering research and inventions in creating new nanopatterning methods and in scaling electronic, optical, magnetic, and biological devices into new physical regimes. His key inventions and breakthroughs include nanoimprint lithography, quantized magnetic disks, self-perfection by liquefaction, ultra-small transistors, high-speed photodetectors, subwavelength photonics, and BioNanoSensors. I'm going to stop there. Let's please thank Professor Chou for... let's welcome Professor Chou.
Yeah. All right. Thank you, Charlie, for such an introduction. And it's a great pleasure to be here and also see many friends I know. Turns out it's my first trip to University of Delaware, and I never recognized it so close to Princeton. So it's a great pleasure to be here. So what I like to discuss in the next 40 minutes, but can I get the light down so people can see it? Can you shut down this light? Yeah, excellent. Okay, so what I like to discuss is some important issues in the nanostructure engineering. And before I start, I want to thank many of my former and current students and my sponsors. Okay, there are many important issues in the nanotechnology, but in my view, I think the first important driving force is that we're trying to make a device smaller, because if we can make a device smaller, then some fundamental physical length scales, classical theory may no longer apply. So that gives us the opportunity to discover and invent. And so here, I want to I put a scale bar from 1 nanometer up to 1 micron. And I look at what are the fundamental length scales in the electronic devices. So I can see that if I make the device size smaller than the optical phonon scattering length, and then I'm going to have the effect of velocity overshoot, and that can make transistor faster. And then if I make a device size smaller than the electron coherent length, then I'm going to have quantum effects to build quantum devices or quantum computing. And if we look at another field, like optics, the most important fundamental length scale in the optics is the wavelength of the light. So if we can make the device size smaller than the wavelength of the light, then there will be a new class of optical devices we never known before. And let's look at another field, which is magnetics. And the magnetic domain wall size is one of the most fundamental length scales. So if we can make the device size smaller than domain wall size, then we'll have a new class of magnetic devices. And then if we look at the area of biology, for example, look at DNA. And one of the important characters of the DNA is the persistent length, which means what is the minimum bending radius of the DNA. And if we can make our nano device smaller than the DNA persistent length, then we can actually stretch DNA into a linear chain. In this way, we can do the analysis of the DNA, and we can do real-time sequencing. So I'm sure you can put your own you can put the fundamental length scales of your own field on this scale to discover the new opportunity. Let me see. Okay, yeah. We also actually making nanocrystals with the feature size smaller than some new fundamental nucleation size. In this way, actually, we are able to find new ways to create nanocrystals on amorphous substrates. So I'm sure there are many, many other opportunities. So in this talk, I want to focus on 3 areas: optics, magnetics, and biology, to show how we can, by scaling the device size smaller than these fundamental length scales, to discover new things. Okay, so in the second driving force in the nanostructure engineering is the manufacturing. Because without the ability to make things, the good ideas will only become a pie in the sky. And so we must have the technology to make them, and also able to manufacture them in a large scale, large volume, so people can benefit. So if you look at the current fabrication technology, the optical lithography, so here is the length scale from 100 micron to 0.1 nanometer here. So the optical lithography today gives us the minimum feature size about 65 nanometer size. And is not sufficient for many things we want to make. And furthermore, the photolithography only can expose a very small area. And then we have the technology of electron beam and the scanning probe. This technology can make a very small feature size, but they are extremely slow. So they are a good research tool, but cannot doing manufacturing. So we need some new technology can manufacturing nano a structure in large volume and low price. So the technology that I originated about 15 years ago, it is called a nanoimprint. So basically, it's using a mold to deform the materials. Of course, you need to have a number of innovations, so therefore you can do the feature size down to nanometer size. And this picture here shows the electron micrograph of the device of feature we made. So you can see that this feature has a pitch about 6 nanometer size, and the variation is almost less than one nanometer size, indicate the high accuracy of this technology. And furthermore, you can actually make a very large mold and press at the same time, a single time. So therefore, it's extremely low cost. And so if you look at the lens bar here, again, you find out a nano imprint can cover almost all the scale size range from 100 microns down to 1 nanometer size, and over a large area, and the very low cost. And so I believe that the future nano manufacturing will be based on nano imprint and plus some other innovative technology. So let's first of all talk about the 3 classes of the devices which we have been developing by scaling down the device size smaller than some fundamental length scales. So let's look at the optics. So first is why we want to make a device in the sub-wavelength range. The driving force is the following. We all know about the bulk optics from camera, our glasses, and many other things, television. And we want actually to get a system, not a bulk, but is on a chip size. And to have this revolution happen, we actually, which is very similar to the revolution we already have had 60 years ago, from vacuum tube to the integrated circuits. So we needed the 2 things. One is the new physical principle, and the second would be the new manufacturing technology. And I'm going to show you that this new physical principle is the sub-wavelength optical element, and the new fabrication technology will be nano-imprint and the similar type of technology. So here's a cartoon of what is a sub-wavelength optical element. So if we have an optical element with a feature size much larger than the wavelength of light, then we can treat the light as a beam. So, just like the operation of the glass. Then if we make the feature size small, but still larger than the wavelength of the light, then we're going to have a diffractive optics, which means one beam coming in, several beams come up. However, if we make the feature size smaller than the wavelength of the light, many new things can happen. For example, the light actually can go all the way back, and it can go sideways, and many other ways, and all determined by our ability to control the epsilon and the mu in the nanometer scale. So let me give you some example. Oh, okay, all right. So before I do that, so let me summarize what the advantage of sub-wavelength optical elements. One, as you're going to see, that the SOEs can create many new optical functions unavailable in the bulk optics. And secondly, is that to perform the same optical function, the SOE can have a form factor 3 order of magnitude smaller than the bulk optics. And thirdly is that unlike the bulk optics, different optical elements need to have different materials. But for the SOEs, we can perform the different optical functions using the same material but different geometry. So these 3 properties of SOEs to make it extremely powerful. And so that's allowed us to do large-scale integration, high-speed, and wafer-scale production and low cost. So, all right. So maybe this is too technical. Let me just go through this slides. So on the left are some typical optical elements we like to make. And all these elements actually can be made by using sub-wavelength optical elements. You can make it large sheets and extremely fast. So the areas which can benefit from SOE, from new optical materials, the integrated optical systems, interconnects, and the solid state lighting, display, solar energy, and the bio, and the atomic clocks. So anywhere you need optics can actually benefit from the SOE. So now let me give you some examples. What is a SOE? How it works? If you remember your optical book, the birefringent crystal is one of the fundamental elements which can make a wave plate. And the classical way to make a wave plate is that to get a crystal, and you polish it, and you need quite a thick, quite thickness to form a quarter wave plate. And in the SOEs, what you do, you start a piece of any piece of isotropic material like glass, silicon. Then you actually create the grooves or tiles. If the feature size of these structures smaller than the wavelength of light, then you can calculate the average dielectric constant. And you will see that the dielectric constant parallel to the grooves going to be much, much larger than dielectric constant normal to the grooves. And for example, if you have use silicon, the difference in index is almost equal to 1, which is about a 4 order of magnitude better than a crystal, which translates that to make a quarter wave plate, rather than you have a 1 millimeter thick of film, you can actually using less than a micron thick. And if you know the technology, you probably know it will take probably several days to do the deposition to deposit a 1 millimeter thick film, but it only take about 10 minutes to deposit a film about 1 micron thick. So that's show you, how important of the application, one of the application for this SOE element. So this is the real example of silicon, the SOE wave plate etched into silicon by using nanoimprint and etch. And you can see that for quarter wave plate, we only have about a 0.3 micron thick is sufficient to perform the optical function. And so this is the optical measurement. And if you have a good the wave plate, you should have a circular pattern. And this is the commercial ones. Actually have this is the SOE. So SOE actually has a much better properties than the commercial wave plate. And the The second example I gave to you is that I still use material silicon, but except I do not use the rectangular grading. I'm using a triangle grading. In this case, the system becomes an anti-reflection surface. The reason is that because these features have much smaller size than much less than the wavelengths of light. So when light coming in, they cannot see individual of the triangle groove, but see the average of the index change from the air to the substrate. And this gradual change of index make this surface one of the best anti-reflection surface you can make. And this is the experimental measurement. For biosilicon, you have 35% of reflection at normal instant. And the reflection will go up as the angle would deviate from the normal. But with the SOE anti-reflection surfaces, the reflection actually well below 0.5%, and it can hold that value up to almost 60 degree instant. So which means that the SOE anti-reflection surfaces not only have very low reflectivity, but also have a very broad band. Because the classical anti-reflection surfaces is by using multi-layer films, by the destructive interference to trying to achieve the anti-reflection. But that approach usually have very narrow bandwidth. But with this approach, a gradual change of index, we have a very broad bandwidth. The third example I want to show is that I go back to the rectangle silicon grading, except I make the pitch of this grading match the half of the wavelength. So therefore, I'm going to have interference occur inside this grading layer here. And the end of the result is that the particular wavelengths have resonance will reflect back nearly 100%. Means, and it's even better than a metal mirror. As you know, the best mirror have a reflectivity about 97 something per percent, 98, close to 98%. But with this SOE, the resonant grading, I can get nearly 100% of reflection. And if you are in the laser business, trying to make a very good mirror, and this mirror is much, much better. And also, if you're working on the long wavelengths, 10 micron something, you do not have very good mirror. But you can use the SOE mirror, very thin layer grading, and give you a extremely high reflectivity, which you cannot get otherwise. All right. So let me give you the fourth example, is that I'm using the grading again, but now this time I'm using Metalwires. And the light is a normal instant to the plane of the wire. So what you see is that the property, how the light interacts with the wire depends on the polarization of the light. If the polarization of the light parallel to the wires, the light cannot see individual wires, but they will see that the current can flow. So therefore, this plane of wires acting like a sheet of the metal. But if I make the polarization normal to the wires, and the wire width is less than the wavelength of light, I cannot drive a current. So therefore, this wire behave like a glass, like a dielectric. And I can transmit 99% of the light through these wires. So immediately you recognize this, this wire grid basically is a polarizer, reflect all the light parallel to the wires and transmit all the light perpendicular to the wires. So this is actually the experimental data here. So you can see that the distinction ratio can be almost 100,000. And if you look at the technology, nanoimprint, and you recognize you can make these wires in large sheets on the wall and anywhere if you want to put it. Okay. Of course, we can make other things. We can make rings, metal rings, bars, and the split rings. And if you, in the area of plasmonics and metal materials, you know that this any ring have a split actually can give you negative mu. And then you're using other metal materials which give you negative epsilon, and therefore you can get a negative the index material. Because of limited time, I will just move on and give you other examples. All right. The other example I want to give to you is that not only we can control the resonant frequency. In fact, we can tune the resonant frequency by tuning the dielectric constant. One way to do that is that we put a layer of liquid crystal on top of the grating, and when the liquid crystal being changed, the index being changed by the voltage, the resonant frequency would change. So basically, we have a tunable filter. And so here is showing you we can tune 21 nanometer range by using the voltage. And combining this tunable filter with a laser diode, for example, we put a traditional Fabrication diode will give you multiple modes because there are many, because the cavity can take many different modes. But by putting a SOE as mirror in front, we can basically pick up one particular mode because the SOE mirror only have a high reflectivity to one particular frequency. And the rest of frequency can passing through with transmissivity almost 100%. And so therefore, we just by simply by putting SOE mirror in front of a Fabrication cavity, the laser, we can make the laser become a single mode. And then if we put a liquid crystal on this the SOE filter, and then actually we can tuning to pick up the different laser wavelengths. So here is the data to show that we can tuning by applying different voltage on the liquid crystal, we can tuning a different wavelengths. And the next thing example is going to show you that about the light extraction out of gallium nitride. As you know, the LED lighting going to be very significant. And when the problem with LED lighting is that because the high index of the semiconductor, only 10% of light are able to escape from the semiconductor, and the rest of the light become trapped, become heat, which is going to actually reduce lifetime of the LED and waste 90% of energy. So one way to get the light out of the semiconductor is to create using a photonic crystal on the on the surface, which actually give you extra momentum and the light allow the light to escape. So here is the example. We have the nanometer structure etched into the sapphire, and then we grow the gallium nitride on top. And then if you do the measurement, and this is a typical blue LED come out, you will see that the extraction efficiency depends upon the size of the grating we use. So for 1 micron pitch, we can get about a 40% enhancement of light extraction compared with the flat sapphire substrate. For 200 nanometer pitch, we get about 70% enhancement of the light extraction. So this become very significant when you're trying to get very high brightness and long lifetime the light emitting diodes. Okay, the other area is making nano optical sensors. And one of the important nanostructure for sensing is the surface enhanced Raman scattering. And there are two problems for the current surface enhanced Raman scattering substrates, or called SIRS. One is that the enhancement is not very high. The second problem, actually really killer, is that typically these high enhancement only at a few random spots. And most of sample are actually has very low enhancement. So the question is, how can we make high source enhancement and also large area uniformity? So we developed a new kind of source, which actually is a three-dimensional antenna coupled with the nano dots inside of the cavity antenna. You don't see them here. And with that, we can get the area average source enhancement to the e to the 9th. And if you look at the uniformity here, they actually very uniform over a millimeter size. Actually, the entire sample we able to fabricate. So that's going to be has a lot of application for sensing and the other areas. Okay, and now let's look at a different field in the magnetics. And we know that the ferromagnetic is very important for memory and magnetic memory and others. If we look at a sheet of ferromagnetic material with a magnetic force microscope, and typically we see the random domains. But if we pattern the magnetic film into a regular square here, you see that this 1 by 2 micron here, we actually have a regular 7 magnetic domain being formed. And for the square ones, we get a 4 closure domain here. They are not random anymore. And furthermore, if we make one dimension of the magnetic material smaller than the domain wall size, then actually we only have a single domain being formed. By the way, these red colors are actual measurement of the material. For example, this show you the nickel bars measured by atomic force microscope. You see the topology of the bar. And then you do the same measurement looking at the magnetic force, and you only see two poles. So what that means is that these nickel bars, once they are being fabricated, they spontaneously magnetize into a dipole magnet. And the reason is that the spin, for the ferromagnetic materials, they love to get spin parallel. But if you have all spin parallel, then you have big poles, so they're extremely high energy. So the way to minimize them is that they break into random magnetic domains. But if you make the device very small, they cannot spin, they cannot change quickly. So then you form this dipole domain here. And there are many applications for this, the magnetic dipoles as the sensors and so on and so forth. One of the application that I proposed about 15 years ago is to create a new type of a disk. I call it quantized magnetic disk. Basically, it has these dipole elements embedded into a non-magnetic material. And if you figure out all the physics, you realize this type of a disk can actually, theoretically, can have a limit over 2 to 3 order magnitude higher than current disk. So in fact, today, all the hard disk drive company is working to make a product out of this type of disk. So within another 2 to 3 years, one of your hard disk drive, if you ever going to use hard disk drive, going to be made of these quantized disk. Of course, for the personal computers, many people today using the solid state drive, but in the data archives, and we still need actually hard disk drive, because hard disk drive still is the cheapest the storage devices for all the devices available today. Okay, so this is a more example about the disks and how they're made. And this is if you look at them, they have different poles. And here shows you why they call the quantized magnetic disk, because the switching of the disk is also become quantized. Classically, you have to use a writing head trying to write each bit. And when the bits become very small, it's very hard because your writing field cannot be confined very small. If you look at all the theory, it's very hard to confine the magnetic field into a small area. And secondly, that you have the disk have many particles. It's very hard to polarize them. But using the quantized disk, everything it becomes single. For example, if you using a head to change over 50% of the bar, it's actually going to propagate on its own and make the entire bar switched. On the other hand, if you only switch part of the less than 50% of the bar, once you remove the field, actually the magnetization will return to its original state. So this is actually like the case you're moving a ball over a mountain, right? This is potential. And so what you need to do to make the ball go to the other side is to move over the peak. And if you move the ball before you reach the peak and release, the ball will go back to the original state. So that's the reason you can have a very precise writing in this kind of disk. All right, so let me move on to the next example is in the biology. And here is the size bar, and here are different biological materials which we can manipulate. So let's focus on the DNA. And we know that when DNA is in a solution, it likes to tangle into the ball. And there is an important parameter called the persistent length. Basically, is the minimum radius that the DNA can bend. And if we make a nano channel with a feature size much smaller than the DNA minimum bending radius, when DNA enter the channel, it cannot bend, so it's being stretched out. So in this way, we can do either optical or electrical measurement of the DNA because it's already being completely stretched out and confined by the channel. And so here is some of the fabrication of the channel. So this is different sizes. This is 35 nanometer long channels. And this is show you that the cross section can make a parallel of them. And so in fact, we can make it on the wafer scale, as shown right down here. And so here shows what happened when we flow the DNA. So here we do not have a channel. So you can see the DNA actually tangle into a ball, very bright, when you put the fluorescent dye on the DNA. But once it enters the channel, it is stretched into a linear chain and flow down. And by measuring the length of the chain, you can actually estimate how many base pairs the DNA can have. So this shows that how the DNA being stretched versus the channel diameter. So for 400 nanometers, you stretch somewhat, but for the 35 nanometer channel, you can stretch almost, the DNA is completely stretched out. And theoretically, you can using this this formula here, and the experiment actually fit it quite well. Okay, and the next thing is that we want to read the DNA. So the key, one of a grand challenge is how can we do DNA sequencing in real time? Because today, actually, doing chemical ways, amplifying gels, and take a long time. So one of the device we proposed of reading DNA is that to have a DNA into a channel and it flows through that channel. Then we put a nano-detectors in a section of the DNA and trying to read the base pair as DNA goes through this channel. So here is the fabrication we made. So we're making glass, silicon dioxide, and then we have the titanium gold of electrodes pair here, and this is the dielectric sealing on top, and this gap is about 9 nanometer wide, and some of them we can make 30 nanometer wide and 18 nanometer to see how the size affect the detection of the DNA. So this is the measurement. For 18 nanometer, we do not see much noise. And for 30 nanometer, we're starting seeing some signal. And for 9 nanometers, we clearly see signal when DNA goes through the channel. And then if we expanded each peak, okay, we see this peak of the DNA. And right now, we still cannot resolve the single base pair. And of course, that's the grand challenge. If we can able to read the single base pair, the world of sequencing going to completely change. So we are working very hard now and trying to hope we can able to read the single base pair as the DNA goes through our detector. However, just ability to detect a single DNA when it goes through your channel using the electronic method already allowed us to making single DNA separator, because we can build nano channels and we have a detector to know when a single DNA goes through. And we can put a valve on this channel, and we can open flush. So allow you to manipulate a single DNA one at a time. So that's actually already offer tremendous of analysis for the tool for the biologist. And because of time, I'm not going to talk about it more. And so this is some other examples. For example, if we trying to look at entire human human DNA, typically is about 3 billion base pairs and about a centimeter long. So you need making very narrow channel continuously centimeter long. And how can you make it? So we develop a novel technology that we can able to do that, able to flow. And all right. So let me have the last probably 10 minutes, probably 5 minutes, talk about the manufacturing technology. So as you know that all the good ideas in the laboratory need a low-cost nanofabrication technology to make them, to commercialize it. The nanoimprint, the reason it's so powerful is because it can have a nanometer resolution, large area, and low cost. So, so here is some examples of pillars, holes, rings, and so on and so forth. So let me say, okay, yeah. So here are the different areas can benefit from nano imprint, from data storage to display, solid state lighting, materials, MEMS, biology, and the semiconductor, and even pharmaceutical, because right now people are using nano imprint to make drugs. The reason is that if you're making drug a certain shape, size, it can penetrate your body better than the others. So there are many advantages there as well. So it's clearly nano-imprint is going to be used by many fields. Okay, so this is an example of a transistor, nanometer transistor, completely by using a nano-imprint technology. And you also can make a three-dimensional patterns, lens. Probably the another important part is that you can use a nano-imprint to directly imprint hard material. Here, actually, I using quartz to imprint a piece of silicon. The trick here is that we're using an excimer laser to melt a surface layer of silicon. And when silicon melt, it has a viscosity actually lower than the water. So you can actually do the imprint less than 250 nanoseconds. And then after silicon cool, you can set a separate mode. So here is the imprinted silicon from quartz mode. And here is actually metals imprinted directly imprinted by the quartz mode. And the viscosity of molten metal is only slightly higher than the slightly lighter than water. So it also can flow very fast. And let's see, the key actually in nano imprint, one key area is how to make a mold. We know that once I have mold, everybody can duplicate easily. So typically people using electron beam to write a mold, but take a very long time if you have experience. So we need a new technology. So the technology we developed is called compositional imprint method. So basically, we started with a linear grading. We can make it into dots. How to do this? Okay, yeah. So here it is. First of all, I'm using the interference method to make a very large area, linear grading. And then I'm going to make a daughter mode by imprint etch twice. And in the end, we're going to get these pillars. And then from pillars, I can oxidize the outside. I get rings. And from rings, I can make a cut. So here, show you. So, okay, I make the pillars. If not round, I can use a melting method to make it melt and round. And then I oxidize it, and I will take the core away. You see it form all the rings. And if you look at the zoom in, these rings are extremely uniform. And then I can make a cut by using the shadowing method. So I cut here, right? And you can also making a squaring, same technique, and depends on what shadow technology you use. You can make a double cut, and people were the reason people want to make a cut is because these metal ring with cuts will give you the negative mu. And so that's a very important element in negative index material. Another new technology actually can cheaply making grading, and everybody can do, even high school kids, is you start with featureless thin film. You sandwich them between the two plates. And when you separate them, actually they start form grading, just like that. And the reason is that when you separate the plate, there is a stress being applied to the film, and the film can break. And if you figure out all the theory, it turns out the best way to break is to form periodic pattern. So this is what happened. And if you look at the pitch of the grading, it turns out the pitch of the grading only depends on the film thickness. It's equal to 4 times of the 4.3 times of the film thickness. So if you can control the film thickness, you can control the grading very uniformly a large area. So the last thing is that if you look at all the nanofabrication technology, you recognize eventually you're going to reach its limit. And what can we do? The classical approach is that, let's find a new method. And then you find out that the new method can solve some of old problems. Meanwhile, introduce some new problem. In other words, no single fabrication technology is perfect. So a different philosophy is that rather than throw away the old approach, is that can we perfect a nano pattern which has the defects? So that is we call this self-perfection technology. For example, if I have a line with the edge roughness, and can we make it become straight and without the edge roughness? Or even better, can we make the line narrower and taller? Right? So the answer is yes. So the technology we developed is the following. We know that thermal melting, the surface tension of the liquid can make a line straight. But also, if we melt these lines, its shape change. It becomes from rectangle shape, it changes the round shape. And also, the flow of the liquid makes the line wider. And furthermore, the flow typically can be done only on the polymers. You cannot do with the silicon or the metal. And so what's our answer? The first solution is that we're using the excimer, the laser, which can melting the surface very quickly without the heating of the substrate. So that's solving the heating problem. And the second solution to solve the spreading problem is that we put a plate on top of the structure trying to melt. So now the top surface is become fixed. So in this case, once it melts, the only way you can do it that it cannot spread, but it keep the side wall become straight, and the top it become flat. And even better, if I have a gap between my plate to the structure here, during the melt process, these lines actually can go up, actually become narrower and taller. So here is the experiment. So we find a very poor sample with a very rough edge. By the spiral process, we get a really straight line. And then we put a plate on top, so you can see the line width become initially 2 nanometer wide, and after the process, only half of the size. And the height is also get increased. And for the this is for the case of silicon. And for the polymers, we have very wide lines, and the short thing, and become very narrow, become very tall, right? So, of course, there are other tricks you can play to do this kind of technique. And all right, so for example, this is you have square. When you melt, you get the dots. But if you guided the dots, actually they are forming vertical pillars rather than a semi sphere as you melt at the free case. So there are many different boundary conditions you can apply, and in that way you can perfect the nano structure in the way you like. So the last example is that after you melt, you actually also can press rather than get a free plate. In this way, you can narrow the gap between the two nanostructures, or you can make a hole smaller. Both actually has many applications in the nano devices. So this is the examples show you that very wide line reduced down to 11 nanometer wide, and this show you how you can reduce a hole size to a very small size. Okay, so of course there are many things you can play, and finally, today actually you can buy commercial tools to do some of this work. You don't need to reinvent the wheel, but enjoy the benefit. So let me conclude my talk. Clearly, nanotechnology offers a unique path to discovery and the innovation. And in order to discover, you have to scale device size beyond some fundamental physical length scales. In the manufacturing, I think the nanoimprint, self-assembly, self-perfection are the key technology. And finally, I believe this is just a beginning in terms of technology, in terms of what we can do. So I'm sure this is going to be a very exciting and growing field. Thank you very much.
We do have time. Is this working? We do have time for some questions. Because we're recording the video, I would like to pass a microphone around to anybody who wants to ask a question. I think I'll take the host privilege of asking the first question, if I may. I was intrigued by all of this. I have a bunch of questions. You're talking about this nano imprint technology.
Yeah.
You said you can do it in large areas.
Right.
Are there physical limits, or how big an area can you do, and can you do it onto flexible materials?
Yes, actually that's what we are pushing. So right now we're doing the roller technology. So we have a roll, and you can continually print on on the sheet. And our goal is to match the printing of newspaper. And if you do not know how fast they print, newspaper is printing 20 to 100 meter per minute. Means it's three, so it's 60 feet to 300 feet per minute. This is today's newspaper printing speed. As newspaper going to die because we have this iPad, and but we can use that to print the many other things. And one thing we are trying to do as the test vehicle, I call the magic wallpaper. So basically, you can put your electronics display, RF sensors, battery, solar cell, all in the sheet. And then you can also print a nano structure on the back, which can stick to any surfaces. And you put down there, they can image or display or transmit. And so that's the technology we are pushing in my lab. Yeah.
So this is really fascinating work.
Yeah.
So from here we see that the nanotechnology have been used very lowly to produce features that repeat itself for many times.
Yeah.
So how do you see this nanotechnology can help the manufacturing of something like a circuit with complex features, but without such a high degree of redundancy?
Okay, I think you asked several questions. The first question, I think you are correct that today many technology developed in the laboratory has not been commercialized. And the reason is lacking the manufacturing. So nano-imprint is a solution for the manufacturing. And then you talk about how you're making circuits. And in fact, you can make circuits by using nano-imprint method. Actually, right now, the largest semiconductor company is trying to developing this technology. But usually, semiconductor taking a longer time because semiconductor industry, taking years to adopt a new technology. So I wonder if that's your question, or yeah.
Thank you for the nice talk. I have a question first about the mode.
Yeah.
So basically, like, how many times you can use each mode? And the second is about the substrate. If anything's wrong, can you easily erase anything on the substrate and then redo another one? Thank you.
Yeah. Okay. The lifetime of the mode depends upon what material you are imprinting. Today, most of material actually is UV curable, which actually is in water, viscosity more like water. And then after curing, it becomes solid. For that case, actually, you can using the mode 10,000 times, something like that. If you do not have many dust. If a dust actually can carry the mode. But then the question is about how you fix the defects on the substrate. Yeah.
The question is more about I want a new structure on the substrate. Can you very easily erase the substrate, the structure already on it, and then still use that piece of substrate? I mean, basically, probably the question about the lifetime of the substrate.
No. Right now, actually, people do not care about if the substrate is bad, they just throw it away. For example, if I have rolling 20 meters per minute, if it's bad, it's bad. Yeah.
When you're talking about self-perfection and reduction of defects, you're actually talking about the defects in the patterns you're creating, right?
Correct.
By melting the silicon,
Yeah.
have you studied what impact it might have on the crystallinity of the material as well as the defect densities of the substrate itself?
Okay. The way, okay, I'll answer you in 2 steps. First of all, the way we melt the silicon is using the excimer laser. And one of the characteristics of excimer laser is that it only absorbed by about less than 10 nanometer of energy, absorbed by less than 10 nanometer of the surface. So only the surface is melt. And the rest of the materials are stay at its own temperature, almost. So that's why people do the LASIK, using the same laser to burn the tissue, because it only burns the surface. And so you can melt only the surface layer of your silicon. And in fact, the quality of silicon, if you start with the amorphous, can become better. And also we see that if we doing this work in the metal quality also getting better because of the melting.
Thank you very much.
Yeah.
Hi. We've been talking about the next generation lithography for over 10 years.
Yeah.
But with the continuous excelling of the optical lithography, what's your comment on when will the next generation lithography will eventually take over? Also, the second question is, when that happens, can you compare your nanoimprint to the extreme UV?
Yeah.
Thank you.
Okay. That's a very good question. This actually is a hot debate in the field. Today, although the optical lithography is reaching its limit, and people have been very clever, able to extend the lifetime by doing different tricks. And I think that's going to be continuing. And there are companies like Intel and trying to push for the EUV, extreme, basically X-ray. And many people in the industry do not think that's ever going to fly. But already over $20 billion has been invested worldwide. And the imprint can be successful based on the low cost. Because today, even using the optical lithography technology, each tool is about $50 million and have a very low throughput. And when you're trying to play the trick to get a smaller feature size, the throughput will reduce by 2 to 4 factors because it has to expose many times. And imprint actually can do much cheaper, faster than the optical lithography. So as I mentioned to you, right now the major semiconductor company is using nanoimprint to making memories, in fact. And they think in the memory world, they can worry less about the defect by using the redundancy, by using the software, because they can check every bit. If the bit is bad, the software actually just use other part, and so they don't care. And so I think in terms of in the semiconductor application, the first application would be the memory. And another thing that people don't recognize, in fact, also the imprint can be used to making optical masks. Because optical masks are very expensive, even to write it, face masks. And in fact, you can use imprint to make a blank with 90, because all the features on the circuits, 95% are the same. They cannot change. And different circuits only change the 5% of them. So you use the E-beam to write the 5% of them rather than write the 100% of them, which is a huge saving.
Let me ask one more question, if I might, again? Let's go back to the beginning of the talk. You talked about
wavelength
optics, and then you did a lot of nanotechnology. Clearly, you're interested in manufacturing. But I was wondering if you've seen any new physics in these suboptical wavelength regimes or in the nanotechnology regimes.
All right. Of course, depends on. There are lots of new physics there in the subwavelength optical elements. For example, I don't know. Okay, the subwavelength optical element is a huge field. I think you have Federico Capasso going to talk about his talk. Actually, his talk only devoted to a small section of the subwavelength optical elements. For example, photonic crystal is one class of subwavelength optical elements. It's a resident type. And then you have the metallic ones, the plasmonic ones. And you have many others. And they're all governed by Maxwell equations, but just have a new set of boundary conditions and give you many new properties which you do not have otherwise. Yeah. For example, solar cells. I can make solar cells much more efficient. I can make many things are much better by pulling these nanostructures. For example, classical one is that in order to absorb light, you need a certain thickness. And actually, I can using, say, very thin, 0.1 micron thick of film to absorb entire light, and over a very broad spectrum. There is many applications for that.
Can you combine that with your imprint technology and make? Can you combine that with your imprint technology and make solar cells at, what did you say, 60 feet a minute or?
That's the one of the goal to make solar cells that fast. And basically, we want to make the magic wallpaper, so and stick on it and change the property. So.
All right, I think we should close. I'd like to thank our speaker, if we can. There will be a reception immediately following in the lobby of DuPont Hall, and you're all welcome, and come talk to Professor Chou in person. Thank you.
Yeah, this is for Lydia.
Okay.
This is her thing.